In this video, we're going to talk about properties of alkynes, those compounds that have a triple bond, and a couple of things, basically acidity and how we make alkynes to be used later on in synthesis problems. So first thing is that when we have an alkyne, we know that we have this triple bond. And this right here is a terminal alkyne. Let me use, in the case of a terminal alkyne, there is an H here. There is a hydrogen. So if we have now an alkene, and let's do this too. These are vinylic hydrogens, but these are then different. And let's do, now I'm going to just explicitly draw the hydrogens because I'm interested in that. But this will be 3 more hydrogens, obviously. Here you will have 3. That's a metal group, and you will have another hydrogen here. But I want to talk about this hydrogen. So here, the hydrogen of the alkyne, of the alkene, and also the alkane. So what do we know about that is that the pKa's of the these compounds. So the pKa of alkynes, terminal alkynes, is 25. The pKa for an alkene is 44, and that of alkenes is 50. That has to do mostly due to the hybridization of the carbon here. This is sp. This carbon is sp2, and this sp3. And what it is, remember when you create sp orbitals, you're mixing one s type orbital with 1p. So 1 out of 2 is s, so we say it's 50% s character. And when you have making sp2 hybrids, sp2, that is, you're mixing one s and 2 p, so 1 out of 3 is an s-type orbital. So about 33% is character. And lastly, when we are making sp3 hybrid orbitals, you're mixing 1 orbital s with 3p, so 1 out of 4 is s, so we say this is 25% character. 25% is character. What that means is that the more s we have, remember the s is s-type is like that, p-type orbital is like that, p-type. So density is closer to the nucleus. The more s character it is, the closer to the nucleus is the orbital. At the end, the orbital where the negative charge will be if I remove that orbital. So I'm going to remove it. So the conjugate base I am removing those is the following. So if I remove that, I'm creating that conjugate base. Removing the alkyne hydrogen. Let's say that I've removed one of the vinylic hydrogens of an alkene. I'm creating that conjugate base. And if I remove that one, the conjugate base is the following. So what we're saying is, where is located the negative charge in the conjugate base? So here at an sp orbital closer to the nucleus, and here at an sp2 at an sp3. So this conjugate base is more stable. That's what gives the terminal alkyne more acidity. So these are stronger acids. All of those, of course, are weak acid. But when we consider these 3 types of, say, hydrocarbons, the alkynes are more acidic. And that will be very important in synthesis. Later, we're going to be using the formation of alkynyl ions in making molecules, in having them react as nucleophile with something else. So it is important to know that. And again, the explanation comes from Orbital. And you may have seen when you study earlier in the course what we call ARIO. We are explaining acid and bases strength using, say, some qualitative analysis. In here, the A is analyzing the atom in which these, for example, in the conjugate base, atom in which the negative charge resides, R for resonance effects, I for inductive effects, and O for the orbital where where you have the electrons in the charge of in the conjugate base. So in here we have explained the difference in acidity of alkynes using mostly, say, orbital, the difference of the hybridization of the carbon where the hydrogen was.